Thank you very much, Holly, and good morning to everyone, and thank you for joining this session. For those of you that didn't join the Wireshark presentation that I did previously, my name is Brian Rushby, and as Holly said, I work for S&T. A little bit about me, that is me. I started my IT career in the British Army back in 1999, back when things were nice and simple as a communication specialist in the Royal Engineers. This was back in the days when the ECDL, the European Computer Driving License, was the must-have qualification. And so, you know, if any of you have got that qualification, put that in the chat window. Let me know. This was the qualification that showed that you could open Microsoft Word in 3 different ways. It was very valuable in the industry at that time. So as technology developed within the Army, so did our systems, and we quickly moved over to an IP-based encrypted network. So I had lots of fun establishing wide area network links across Afghanistan, Iraq, to name a couple of places. Unfortunately, all good things come to an end. I left the Army after 16 years, and I was fortunate enough to get a gig with Cisco on their graduate program. Unfortunately, that finished earlier than was expected, and I didn't quite fancy a move to Belgium to work in their TAC. So I ended up joining Virgin Media as a technical project manager. Had some really enjoyable years there. And now I find myself in my current role with Systems and Network Training, or SNT, where I teach Wireshark, CCNA, routing and switching, as well as foundational courses for all types of engineers, and of course the LINX accredited engineer courses as well. So that's my details, and this is what we're going to be covering today. So the Internet Protocol version 6, or IPv6, or 6 if you're really cool. Okay, so this is what the presentation is going to cover. So we're going to look at some origins and the motivation for IPv6. I think we all know what the big one is there. Just turn my phone off. It is on silent, but someone's still ringing me. We're going to do a comparison with IPv4. So we're going to look at the IP header and compare that with the IPv6 header and look at some of the improvements and efficiencies that have been made. We'll examine some of the different address types that we commonly see with IPv6. We're going to have a little look at DS Lite as well, just a brief overview. And this is really popular within the ISP provider offerings at the moment, how they're utilizing IPv6. And then we'll do some general network configuration. We'll be using Cisco routers. So if you're not familiar with Cisco, remember the commands are not so important, but we're just sort of the general gist. If you are looking at studying for CCNA qualifications, you'll find that section really, really useful. So let's move on to our origins and motivations. So let me switch my screen. There you are, whiteboard. Okay, so just looking at some chat windows, that stuff there. Right, okay, so origins and motivation. Well, I think we all know that the big motivation, having a little technical issue here, just bear with a second. I seem to have lost the use of my pen. Let's see if it's going to come back to me. Ah, there you are. Little tinker. Okay, so the major thing with IPv6 is we needed the additional address space, didn't we? Okay, the address space was a massive motivation for moving to IP version 6, which seems strange when you consider that actually with IP version 4, we had as many as 4.3 billion IP addresses. And at the time, when that was produced, we thought, well, that's going to be enough for us. But it quickly became apparent as the growth of the internet became massive and the technological advancements and our vision for the future that we would need more address space. So the concept was come up with IP version 6. which is going to give us a massive 340, and this is a real number, undecillion addresses. We'll look at that in a bit more detail later on, but it's 340 billion IP addresses, more than enough for everyone on our planet several times over. If you want to do a little comparison with that, if any of you have been on any of Jeff Carroll's presentations, he gives a great analogy, and I'm going to steal it, so apologies, Jeff. If we was to weight all of the IPv4 addresses, and we said that they each weigh 1 gram, all of the IPv4 addresses would weigh the equivalent of about half of the Empire State Building. So quite a few there, quite weighty, I would say. Now, if we compare that with IPv6, I think you can get where I'm going with this, or maybe you won't. So again, all of the IP addresses weighing just 1 single gram. Well, this would weigh 56, not 56 earths, actually 56 billion earths. What do you think about that, Holly? Does that blow your mind?
That does. I just can't comprehend that, to be honest.
It's a massive amount of addresses. So I've had this argument several times with people where I will stand by and say, there is no way that we will ever run out of IPv6 addresses. It's just impossible. And I get a little waggy finger and they'll say, no, you can't say that. It could happen. Well, I think we would be long gone as a race by the time that would ever get close. It's a massive amount. But it's not just the massive amount of numbers why I can have that argument. The way that we allocated the IP version 4 space is actually not very efficient. Not to criticize, but in hindsight and everything, all experts. So if we look at IPv4, I'm sure you all know that we break it down. Just change that one. We break it down into some classes. Excuse my handwriting. I'm going to show you it doesn't get any better as the presentation goes on. Okay, so just as a reminder then, our Class A networks will be any IPv4 address that starts at 1, we don't use 0, as I'm sure you remember, going up to 126. 127 is reserved for our loopback. So our Class B range starts at 128 and goes up to 191. Our Class C, 192 up to 223. Then we've got Class D where we hit our multicast. And then we've got our experimental or reserved, which starts at 240 and goes up to our maximum number, which is 255. Now, again, looking back with, eyes wide open and understanding what we know today, we could argue that, this probably wasn't the best way of doing it. We've got a massive amount of IP addresses here assigned to multicasting. We've got a massive block here that we don't use at all. I can give you an example where the Amateur Radio Association, and again, if there's any ham operators in the audience, just please feel free to speak up, announce your presence in the chat window. The Amateur Radio Society, I think they're called, or organization, doesn't really matter. They got allocated a massive amount of IPv4 addresses back in 1981, which was the year that I was born. So in 1981, they got given a 44/8 range. So basically 44.0.0.0 all the way up to 44.255.255.255. You know, 16 million addresses given to the Amateur Radio Society. They'll never use it. They know they'll never use it. And they actually, I think it was middle of last year, they actually sold just a quarter of that space to Amazon Web Services, to AWS, raking in a cool $50 million. Because IPv4 addresses are rare and contiguous space is rare. Now, in November last year, it was announced that all of the, well, certainly for RIPE anyway, our European Network Coordination Center, all of the IPv4 addresses had been issued. Now they will recover them and they will reissue them, but really there's no use case for it. When it initially happened, RIPE had a massive waiting list, lots of organizations waiting for additional IPv4 addresses. If you go onto the RIPE website now, so feel free to do it, if you have a look at that waiting list, well, it was last time I checked, it's now empty because people are understanding that there's really no benefit to sticking with IPv4. It's easier, our address space is cheaper, and we can actually get a lot of efficiencies and benefits by moving to IPv6, which hopefully we'll learn some of those today. So if we look at this, what I mentioned here, we can actually say that of all of the IPv4 addresses that are available, that 4.3 billion, we're obviously rounded up a bit, 4.3 billion, only around 15, maybe 15 to 20% at a push was actually used. You'll see that when we look at the addresses with IPv6 a little bit later on, that we're going to be a little bit more efficient with its use, a little bit better with its allocation. Apologies, frozen here. Okay. So I put this slide in just because I like it, really. So if you think about, you know, when IPv6 was formally published as an RFC, it was just late 98, so say 1999, about the time I joined the army, really. But if we think about, I mean, this is, you can take, this is, it's an American survey. It was the Washington Post, I believe. I did put a credit somewhere. 2000, it wasn't until the year 2000 that more people had some internet connection that didn't have any at all. Okay, so we just think about the actual growth that we've experienced across the world. It's absolutely huge. So I mean, I'd like just to, as a little bit of you know, sort of participation. If you just stick in the chat window now, just have a think about, you know, what IP addresses, what devices that we would have, you know, when we initially got onto the internet. Now, I think you could probably say that we'd have maybe a single desktop PC that would be attached with an Ethernet cable directly into a modem, something like that. We wouldn't have much more than that. Whereas now, if I just look around my living room here, I can see 4, 5, 6, 7, 8. That's 9, including my phone. So there's been 9 devices straight away that's got an IP address. Holly, how many IP addresses have you got? Do you think? How many devices will be getting an IP address?
I think when I counted last, it was about 21, 22, and that was in my whole house.
So quite a few.
Yes.
Quite a few. So we can see that there's a massive amount. So I can see there's not many people adding anything to the chat window. So I work blog a dead horse. There's a lot of factors at play that has accelerated the exhaustion of IPv4. The main ones is the rapid growth of the internet and the rapid growth of technology. obviously that we can say poor allocation, as I said, we're all experts in hindsight, and maybe being quite liberal with issuing those IP addresses allowed us this growth, and it got us into the position where we are now, where we've got some great technologies and great businesses and industries starting. So, but what we do have, or what we have, is a few mitigations. So one of the first things that it was identified that we could do is we could do network address translation. So for those of you not familiar with network address translation, let me just world's smallest laptop. Let's just make him a bit bigger. So let's say I've got my home router. I've got the promised land, that is the internet. So what we're able to do is, instead of having all of our globally assignable IP addresses and using all of those, we're able to implement network address translation, where everyone will have a private IP address that won't be used on the internet, but we'll translate that to a routable IP address. So for example, let's just make this a little bit bigger. We'll look at the private ranges in a second. But for example, I can have my inside address, and I can then translate it to a routable address. Let's say going to the promised land of somewhere. Make that a bit different. So instead of me using all of or issuing all of my devices a routable IP address, I can just issue a single one, and I could do static one-to-one mapping. Now, obviously that's not ideal, because then we might have a limited pool of IP addresses that we can use for that assignment. So that's when we come up with network address port translation, or port address translation. Okay, so what we'll do this time is we're going to take our initial IP address, but we're also going to add on the source port information. So now when we've got multiple devices connecting, we can distinguish between them. So let's just pretend we've got some other devices that's on the inside here, that creative license. We can actually map them to the same IP address. And we distinguish between them with that source port number. Okay, so quite a straightforward but fantastic method of us saving on our IPv4 addresses, using them more efficiently. And we'll see how that's going to kind of how that works when we look at DS Lite. So that is still used for IPv4 to 4 mapping. So another one of the big mitigations, RFC 1918, about private address ranges. So each of the classful networks, Class A, Class B, and Class C, were each assigned a block of addresses that would be used for this purpose, for using as private address ranges. So anyone is able to use these. And there'll be multiple uses of them across the internet, but it doesn't matter, because we're going to translate them to a unique address for when we're actually going onto the internet. So these are not routable. Not routable, private. So our class A range, and I'm sure we've all seen, is 10.0.0.0 with a /a. That means that we've got everything from 10.0.0.0 all the way through to 10.255.255.255. Squeeze them in there. Great, they're all private addresses that we can use. Our class Bs, we've got 172.16.0.0 with a /12. So that's telling us that our private address range for class B is 172.31.255.255. And those of you that are looking at that, oh, that's not, that'll be the end. Let's see if it'll pick up. Obviously, not the start. Let's put the start on like we've done with the one before. It's obviously just the same. To rub that out because my OCD is going to go nuts. Okay, and for class C, which is what we'll probably see on our home routers, is 192.168.0.0/16. Obviously, I'll start going all the way up. Okay, that is 255. Okay, so we've got these ranges that we can use. So just a quick point, which does get a few people sometimes. So class A, obviously a class A, forgetting about a private range, its classful address, or classful mask, should I say, is a /8. Class B is 16 and class C is 24. Okay, so just remember, just because we've got that /12 there, we're using that prefix notation, that slash notation, that's just defining that is the range of IP addresses that are included within that range. It's not saying for a private range, you have to use a /12. It's a minimum of 16 and usually will be used with additional bits as well. And of course, we've got subnetting, we've got VLSN. All right, so again, if you've not done any subnetting for a while, let's just do a quick example here. So we've got the original IP address that we've been allocated, this 200.10.10.0 with a /24. So again, at the moment, this IP address, it's will be a network of 254, okay, because we've got 256 possible addresses, and we're going to take away two, one for the network ID and one for the broadcast ID. So if I want to subnet that, let's say that I'm going to change this, and this is going to become /28, for example. So let's see what networks we would get from that. Well, the first thing that we need to work out is we need to work out what the interest in octet is, and we need to work out what the count value is, or the chunk, or the interval, however you want to call it. We always start when we're subnetting with the original IP address that we're using. All I'm going to do this time is just change that to a /28. Okay, so to work out our interest in octet, we see where does the subnet mask finish? So in this case, a /28 is going to be a 255.255.255.240. So because it's .240, because it's finishing, that last subnet bit is in the 4th octet, we're going to count in the 4th octet. And because that last subnet value, okay, so the last subnet mask bit is 16, then we're going to count in 16. We can do that another way. So where we had our dotted decimal notation mask and we said 255.255.255.240, we can just take that 240 away from 256, giving us 16. So that means that my next network in this range is going to be 200.10.10, because they aren't changing, .16, and that's a /28. And then we can just count up accordingly all the way until we get up to 240, which would be my last one in that range. I'm not going to go through all of those, because you're going to miss the good stuff there. So just as an example then, so obviously my first host here would be 200.10.10.1. My last host in that range would be .14, and my broadcast ID would be .15. Okay, so a way that you can do this, just as a little tip, once you've written down your network IDs, remember that these are going to go all the way up as they are until we get to 240, unless we change the mask, which we can do. I'm not going to go into that now. What we can do is use the next network ID and work out the broadcast. So if we say a .31 is one less than that .32, because what can happen, and it happens to the best of us, is that we tend to forget about the broadcast ID, don't we? So we say, right, okay, so my first host is .33, and all right, so that's 48, so last one's 47. And that's fine, because usually with our network equipment being fairly advanced, it will say, negative Ghost Rider, that is not a good mask for me. You need to pick a better one. So it will tell us that it's wrong. But obviously for our documentation, when we're writing things down, we don't get that sort of built-in check device, right? So we have to do it ourselves, unfortunately. So a good way is to work out the broadcast ID first and then count one back to work out the last host. That way you won't forget about it. Okay. So has anyone got any questions so far on the origins of IPv6? So remember, the main driver for it is that address space. We've talked about how we've got into that situation where the rapid growth and the rapid, not just the internet, but technology in general. And when we've looked at the mitigations that were brought in. And if you think about it, we've only just run out, sort of almost 20, 25 years after this was identified. So, we can criticize maybe some of the allocation at the start, but there's still, the people at the front of the IETF and its contributors still very forward thinking and saw this well in advance. Any questions at all, guys? Okay, I shall take that as a no. And let's move on to the next section. So we're going to have a little look at the comparison with IPv4. So again, we've mentioned some of this, but we'll just quickly scribble it in here as well. And Holly, just to confirm with yourself, if I send a copy of this presentation to you, can you make this available for everybody?
Yes, of course we can. We can put it on the Learn with LINX webpage.
Yeah, I think that would be useful. Well, hopefully people find it useful if they're doing any sort of studying for anything. Okay, so let's do a little comparison with IPv4 then. So we know that IPv4 has 32 bits, which is where we get our nearly 4.3 billion addresses from. With IPv6, we're ramping that up. We're times it by 4. We've got 128 bits in total. And we've already mentioned about our addresses. So we've got 4.3 billion IPv4, whereas we've got 340 undecillion. And as I keep saying, it is a real number. Okay, so an example address, again, we'll just put this one here. So an IPv6 address can be very, very big. Very, very big. Now, obviously, I'm sure you're all aware that we can do some abbreviations, which is good because we're going to be doing some in a minute. I have to keep counting, making sure that I've got this right. Okay. That's what we could have if we write everything out like that, which we're not going to ever do, right? We don't have to do it. We can abbreviate it. Our devices understand that abbreviation, so it's all good. The address format, if you get asked that, so we've got dotted decimal notation for our IPv4 addresses. And we've got colon separated. I'm sure this is why some people don't go to IPv6. Hexadecimal. Because it does seem that they tend to use the most crazy terminologies possible to almost try and scare people off. And there's really nothing to be scared about with IPv6. Okay, so colon separated hexadecimal. So where we've got these numbers here, that's not a decimal number like we see with an IPv4 address. That 2 is made up of 4 bits. That 0 is made up of 4 bits. They're just not turned on, that's why it's 0. Okay, so let's have a look at the sort of the basics of the compression and expansion of an IPv6 address. Now, and again, this is stuff that is useful for us when we're doing configuration and when we're looking at documentation as well. But when it comes to configuring our devices, it's going to do it automatically for us. If we put this in completely, for example, it would understand it. We can enter the compression as well, and it would also understand it, as long as, of course, we do it properly. So if we have a look, there's 2 things that we can do when we're going to compress an IPv6 address. And we've got a few examples of compression, and we've got a few examples of expansion as well. So the first thing that we can do is we can drop leading zeros out of the equation. So obviously this, the first 0 in the first hextet, and I'm going to call them hextets, and I've heard them called some different things, but that's fine, is not a leading 0. These 3 are leading zeros. So we could take these off. We could take this one off. We can't take any of these off in the 5th hextet. We can take this one off. Okay, and we could rewrite that IP address as 2340 colon 0 colon. I've realized I've missed I've put a dot there. Never mind. And so on and so forth. What we can then do is we can take any blocks that are all zeros and we can just shove them together. So where we've got these in the 2nd and 3rd hextets, we can actually just abbreviate those with a double colon. So our new and improved, shortened, and much easier to handle address is going to look like this. Still quite bulky, but the way that we can do it, and in reality, obviously this is just an example. The way we can do it in reality is we can make sure that we put our zeros in where we want them to, and to compress it in such a way when we're using things like unique local addresses, which I'll come on to in a little while. Okay, so here we've got an example where we've got 2 separate blocks of zeros, and this is where one of the first rules comes in, really. So we've got this double colon that we can use. That's going to shorten one whole block, but we can only use it once. We can't use it twice. Now, if we think about it, our machines are fantastic. They do a lot for us. I love them to bits. I'm a big fan. But if I was to say this, and then I was to try, or my machine was going to try and put that back together, it would have to ask me a question because it wouldn't know where to put the 3 blocks of zeros and where to put the 2 blocks of zeros, or the 2 hextets and the 3 hextets. It wouldn't have any idea. So we have a rule, because we need rules for this kind of thing. And we need to say that we're going to use it on the biggest block. that way we're making a standardization where everybody knows, and our machines, more importantly, know what we're talking about. So this time we would just say 2340 colon ABCD colon 0 colon 0 colon 1 2 3 4. So I'm still going to drop off my leading zeros because that's that other thing that I can do, but I still need to leave that non-leading zero in place so that when it comes to put it back together, which we'll look at shortly, or expand it, I know how to do it. Okay, the last example that we've got here, again, I can drop off my leading zeros. I've got 4 big blocks and 2 more leading zeros. And hopefully now you are very adept with IPv6 compression. And there we go. Okay, so much easier for us to do. And now we're starting looking at the same sort of size as an IPv4 address, aren't we? Okay, so I'm not going to go through this one because we've just pretty much gone through that example already of 2 double colons being used. We can see that it doesn't work. We can't do it. If we want to expand this one, then here's where we need to understand that we've got 8 hextets in total in an IPv4 address. Remember, each hexadecimal character represents 4 bits. And I've got 8 hextets in total. So all I need to do is count how many I've got here. How many can I see? Well, I've got 1, 2, 3, 4, which means that this double colon is hiding 4 hextets of zeros. So just bear with me. Sing yourselves a little song. Could do that elevator music back, Holly. That's why I write this out. Just check that. Yeah. Okay. So we can see that we've got a massive. Oh, I've put an extra one in there. Oh no, I haven't. I've just got that one in there. Okay. So that's my 4 blocks that was being hidden. This one just confused me a little bit there. But obviously we dropped the leading zeros from this one. Remember, we still needed to leave that non-leading zero in position, so we could work out it was there. In fact, the way that I've done that, actually, where I've got that example from, that's what's confused me, because this could be done away with as well, couldn't it? So really, we should have 2340 colon colon 1 colon 2. All right, so hopefully you all picked up on that, and as I did. Okay, so if we have a look at the last one here, and again, it's just a case of working out how many hextets that we've got in position. So here we've got 1, 2, 3, 4, 5, 6. So again, tells me that this is representing 2 blocks of hextets. And I will edit that example before I send it off to you, so you'll be pleased to know. Okay, has anyone got any questions on those? Just stick them in the chat window. So it's very straightforward, guys. So, you know, we can drop leading zeros, or we can, and we can compress blocks of complete zeros of hextets together with a double colon in position. Okay, we've had a look at why we can't use more than one and why we're going to use it on the bigger block so we have that standardization in place. One other thing that I want to mention is about capitalization. So you can see here that I've used lowercase for the typing. Now, there's nothing wrong when we're documenting our IPv6 addresses. Let me just do a little example here when I'm typing. So there's nothing wrong with using our capital letters in such a way. And obviously, when I'm using something like this, again, not a problem. But we do have, it is stated within the RFC to say that if we're kind of handwriting our addresses out, it's a good idea not to use capitalization, to use lowercase. And the reason for it is this: when you've got people like me that can't handwrite very well at all, we can see that when we use capitals, some numbers and letters could eventually be mistaken for the other. Okay, so that's just an example of that. So if we said, if you look at it, the same ones together done in that way with the lowercase, you can see that it's not going to be it's going to be very hard to not be able to distinguish against those. Not impossible, but it's it should be much better. So if you're writing these IPv6 addresses out, good idea to use lowercase. You know, if you're passing a note to an engineer to configure something to you, hopefully you're not, because hopefully you're using proper change processes within your companies and you're not doing change requests on the back of fag packets. But if you are, then make sure you use the lowercase letters. Okay, so we've kind of said already about the benefits of IPv6, about the massive amount of address space, but it isn't just that. And we've said about how it can be off-putting to people with because they see this massive address and they get a little bit scared. But if you actually have a look, so most IPv4 configurations, we might have to put something like this in with our subnet mask. We might have some versions where we can also use the prefix notation, maybe. Okay, depending on the vendors and everything. If we think about it in IPv6, we don't have to use a dotted decimal subnet mask. We'll need to use the prefix notation, okay, and define which part's the network, and that's okay. But where this is being used with IPv4 quite regularly, what we'll see in IPv6 is probably something like this. So not to be pedantic, but really there's not that much difference in the amount of characters that we've got to input to do our configuration. It's really nothing to be scared about, and it's definitely not a reason to delay getting across to IPv6 as soon as possible. So I'm just having a look at the chat window, and I can see a question from Willem. Hi, Willem. As you do not get a 0 in hex, is it really a problem? Well, we do get a 0 in hex. That's the issue. If we don't have any bits turned on, so if we think of a hex, so let's take our first hex character. Let's say that it's a 2. Okay, so we've got 4 bits behind that 2. Okay, so we can see that this 0, the first 0 is 8410. So that least significant bit under the 1 is the placeholder that tells me that that 1 represents 2. And then we've got 4 and 8 are in position, but then the value's not being taken for them. So if we have, if we look at the next bit, let's say that this next hex character is a 0. That's going to still represented by 4 bits. It just means that they're all turned off. Is that clear? I see, okay, the letter O, not a number. Well, obviously we haven't got the letter O, but it's the number 0 that looks similar to the letter D. And again, we're talking about specifically really when we're handwriting these things out. So it's a recommendation from the RFC to, you know, if we are handwriting things, you know, to use lowercase letters when we're doing that. And again, when we're using our documentation, you'll see within the RFC that states about using lowercase. We use capital letters all over it because it's typed, because it's printed, and it's no problem at all. And no problem, Willem, that's fine. Okay, any other questions at the moment? If not, let's move on to a little bit about IPv6 addresses. So we're going to talk about how we're going to learn about an IPv6 address. Well, it's pretty much, obviously there is some new mechanisms, but we can still do it in the traditional ways. We can learn dynamically using DHCP version 6. We can statically assign our IPv6 addresses exactly the same way as we can do with IPv4. But what we can do that is different is we can use a thing called Slack. Okay, and this is stateless address automatic configuration. So what this is going to allow us to do is it's going to assign, our devices are going to assign themselves its own IP address without DHCP. So it's going to do a router solicitation. It's going to find out about the prefix that it needs to use. And then it will create the interface portion of the address by itself. So where we've got the first 64 bits that are generally used as the prefix, and we've got our second 64 bits of the address is generally used for the interface configuration. Now, there's a couple of methods that we can use to do that, to generate that. And one of the methods is EUI64. Okay, so this is an extended unique identifier. Okay, extended unique identifier. Now, this is initially there's no problems with this, and it was being used quite often, and it is still used, and it is still taught within a lot of the certifications. But let me show you why maybe it's not such a grand idea. And there is, you know, RFCs that are now produced about potentially privacy concerns by using this method. So the way that EUI64 works, as I mentioned, generally the interface is going to be 64 bits in length. Generally. Now, obviously, there's, you know, some transition mechanisms where we won't have the interface at all because we're just yamming an IPv4 address into an IPv6 format. So, you know, I understand that there's some differences, but generally that interface is going to be 64 bits in length. So what all of our devices should have already is something which is 48 bits long. Feel free to yam it in the chat window if anyone's keeping up. We should have something that's unique on our devices, and that is the MAC address. Okay, so our MAC address, but it's not quite big enough. Okay, it's 48 bits. Okay, it's 12 bits of hex usually. We'll see the format that we'll see it in. So not quite big enough, 48 bits. We want to get it up to 64. So let's just put a quick example in here. Okay, so we've got our sudo MAC address here. So what we need to do, so obviously this is 48 bits in length. Remember, it's 12 bits of hex. So what we're going to do is we're going to split it in half, and we're going to place in an additional 16 bits to get us up to that 64. So let's put some little steps in here. So we can see, so step one, we've not really done anything. That's just our MAC address as it is. Step two, what we're going to do is we're going to insert some additional hex. So let's say we've got our EF here, and then I've got my 1, 2, 1, 2, 3, 4. What we're going to place inside there, use green, is F, 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 E. Okay, so we're going to do that on all of our EUI addresses. We're going to put in that additional 16 bits, those additional 4 hexadecimal characters. And then for our step 3, what we're going to do is we're going to examine the 7th bit. Okay, so the 7th bit we're always going to find here. Okay, remember that the first character is 4 bits, so the second character contains that 5, 6, 7, and 8 bits. So if we have a look at B, so B, as I'm sure you all know in hex, is 11. So if we have a look, let's just write that out here. So a B is 8, 10, 11. Hopefully everyone's keeping up with that. So that's what it looks like initially. What we're going to do is we're going to change it. So we've still got our 8.4, the values that haven't changed at all. What we're going to do is we're going to flip the 7th bit. So this time, it's going to say 1, 0, 0, 1. So whereas before it was saying 11, represented by the letter B, it's now going to go down in value by 2, and it would just be represented as 9. And you'll see that whether that bit is on or off, we're basically going to add or take away 2 from the value of that second hex character. Okay, you'll see that pattern all the time. So what we are left with is A9, C, D, E, F, F, F. See where I am? Yep. F, E, 1, 2, 1, 2, 3, 4. And if we look here, now we've got 64 bits. Yay. That's what we need. No, it's not good. Okay, let's have a look why. So if we're our MAC address, we should all, hopefully we know that this part here in reality is the OUI, the Organizational Unique Identifier. So that is something that is registered by a company that says, okay, so these first 24 bits of the address represents Cisco, represents Palo Alto, represents Checkpoint, for example. It might even identify, further down than that, that it's a Cisco switch or a router or a Dell laptop or shuttle box or whatever. That second 24 bits is a unique serial number associated with that OUI. So if I was a hacker, and I'm not, but if I was, I could have a look at that interface ID. If I could capture that traffic, if I'm, I can sit myself in the middle of a communication, and I can work out from that MAC address, if it was a real MAC address, I can, what sort of device is communicating. I could also because of that serial number, I remember, oh, obviously this bit's flipped, but it's not hard for me to, not that bit, there's a wonky error. Obviously that bit's flipped, but I can just flip that back to get the actual OUI. It changes the same way every time. So with that serial number and that information, I can see exactly what device at least it is. It might be someone sharing a device, but it's likely to be the same person. So I could follow that. I could follow that MAC address. I could chase that MAC address. I could track potentially the movement of that device across the world. So we have new and different methods. So I think it was from Windows XP. So we're going back quite a while. Windows won't use this. So Windows will randomly assign the secondary portion for the interface. And I think Linux devices, they still use the MAC address as a seed, but they'll run it through a mill of different maths, you know, to get up to change that information. So hopefully that's clear. So the way that it will work, very straightforward here. Let's so we've got two devices connected to a network, and we'll say device B is going to send a message and say, basically to himself. So you might remember from IP version 4, we had a concept called a gratuitous ARP message. It's exactly the same process. So when we get our DHCP IP address and information initially in IPv4, we'll send 3 gratuitous ARP messages. And if someone replies, that indicates that there's a duplicate IP address on the network, and we will reject that, that DHCP offer, and we'll ask for another one. So the way that Slack will work is he will send a message into the network. Hello me, and he'll listen for a response. If nobody responds, then that's all good. He can fix that. He can fix that in place. If someone responds, then he'll just generate another one. Really, really simple. Really simple. And another reason why it's better for us to use random, a random method to generate that interface rather than using the MAC address, because we can just pick another one. And we'll see, and we won't go into detail on it today, but you can see that we'll change these interfaces over time as well. Okay, we'll have a deprecated state. We'll generate a new interface. So we're not using the same one all the time. Again, increasing our privacy in IP version 6. So before we move on to looking a little bit between the headers, just want to quickly go over some message types. Okay, so I'm sure that you're all familiar with a unicast address. So a one-to-one address. I have a broadcast address or a broadcast, my favorite, which is one-to-all. We have multicast, which is one-to-many. And if I give myself a little bit more space, I'm stealing in to the next bit. We've also got anycast. I want to cover these very quickly. Okay, so anycast, just to say this, okay, this is what I call it, one to nearest. Right, you might hear it be described elsewhere as one to one of many, or one to the one of closest of many, and it's really complicated. you're going to the nearest one. That's it. One to nearest. It's a much simpler way of describing it. Okay, the way that Anycast works is I can have the same IP address given to multiple servers and services across the world. Generally, they'll be giving the same offering, whatever it is. It might be a Netflix server that's going to play Breaking Bad for me. All over the world, I'll just be routed to the nearest one. So if I'm on holiday in America, I don't want to go through the British or whatever the nearest one is to us in the UK. I'm not sure. And the same for Amazon Prime, everything. All of it is done in the same way. So we can just go to the nearest one. So it gives us a couple of different things, really. Number one, speeds things up. Number two, it gives us a very, minor sort of DDoS protection as well. So if there is a compromised botnet out there, instead of us pointing something to one site, if we're using something like Anycast where you're not guaranteed to be routed to that individual device. So there is that kind of mechanism as well. Now, again, Anycast is not specifically brought in for IPv6. Okay, it is RFC'd for use in IPv4. It just is not used very often. Okay, so again, it's not, what you read is not specifically for IPv6. It can be used for IPv4. We know about multicast, one-to-many. We're going to be utilizing multicast a great deal more in IPv6. And the reason for that is because in IPv6, we don't have broadcast anymore. Okay, so we're still going to use a multicast in that we'll send to many devices at the same time, but we're not going to send to all devices at the same time. So instead of us bombarding every single NIC interface with a message that they might not need, we can give it a little bit more granularity. So we might say, okay, so we're going to send a message to all of the routers that are on the network. We might send a message to all of the nodes that are on the network. Looks a little bit like broadcast, but it's not quite the same. Okay, and again, yeah, great answer there, James. I've just seen on the chat window. So yeah, obviously with DNS, we can see that being used quite often in that way. So as I said, it's not strictly IPv6. Okay, so what I want to do is just do a little comparison now between the two separate headers. I'll tidy this up before I send it over, guys, so don't worry about that. So we'll see straight away when we look at that there's a lot of information within that IPv4 header. And although it is obviously a bigger header, the IPv6 header, it's a lot more straightforward. Okay, the majority, it's a 40-byte fixed header. The majority of that's made up of the addresses. That's 32 bits worth of it. Okay, they're both going to start with the version ID. That makes sense, doesn't it? We need our we need our devices to understand what it is that they're working with, and whether it's an IPv4 packet or an IPv6 packet. So that's still going to be there. What we don't have is we don't have what's called the internet header length, but we don't need to add that because it's a fixed length. The DSCP, so differentiated services code point, or diffserv, is basically our quality of service. And that's just our traffic class, basically. Our explicit congestion notification, that works in tandem with TCP. We're going to see that possibly used within the next header options, but we're not going to see that as an individual field in IPv6. Where we've got the total length, in IPv4, this would describe the header size and the payload. In IPv6, this is just going to describe the payload. We already know that the header is 40 bytes in length. The identification, flags, and fragment offset are really used for fragmentation in IPv4. So each packet would have an individual identification, and we can set specific flags to say, yes, you're allowed to fragment this packet, Mr. Router. And then when those are fragmented and they get to the destination node that's putting those fragments back together can see where they're supposed to go with that fragment offset. We're not going to go into any more detail than that. But what we'll find with IPv6 is that a lot of this can be put back on, onto the source, so onto the sender. We can send back and say, actually, you need to do the fragmentation yourself, or rather, you need to send your packets in a smaller size. There is an option of doing fragmentation within the extension headers. We're not going to go into detail on that here, but just understand that it's available. And to help us with that, in IPv6, we have the flow label, which is going to be describing, that unique flow of traffic. Okay, the time to live field and the hop limit is really going to work in exactly the same way. Remember that time to live or the hop limit, every router that we go through, it's going to be decremented by 1. Okay, we may also see if you're being held, so if you're experiencing congestion, then that time to live can also be deprecated while it's in the same router by 1 for every second of congestion that it's experiencing. And if we get if we have in fragmentation and our end device that's waiting to put that back together, it will use that time to live as a count. So if it's, if that runs out, it will say, fragmentation needed. You didn't get it to me quick enough. Try again, mate. The protocol field and the next header is pretty much the same thing. So where these often get confused is we think that the identification field in IPv4 is what tells us what's inside the packet. It's not, it's the protocol field. And in IPv6, we just call it the next header. So if I'm carrying a TCP segment or a UDP datagram, it's going to be, it's going to tell me there basically. And if I've got an additional header, then again, that's where I'm going to tell people about it. Obviously, my source and destination address, exactly the same, except in IPv6, it's going to be 4 times bigger. Right? No other difference there. And we're not going to have that options field. That's now been taken out and it's been added into as an option within the extension header. Okay, so we can add some stuff in there if we want to, and that will just be an extra header and bolted on. And we'll see that for things like VPNs. What else? Something else I wanted to cover. You don't have anything in you. So the checksum. You see that we don't do the checksum anymore. So initially when IP come about, yes, we had that in there, but we can do this checksum, and we do this checksum, in many different ways now. We have TCP has its own checksum. Obviously Ethernet has it within the Ethernet trailer and the frame check sequence. So we can do the checksum in different ways. Even a UDP header has an optional checksum within it. Okay, so people often ask, and I'm definitely running out of space here, so let me just slam this across a little bit. So people often ask, and they'll say something like, will we ever be fully on IPv6? When, or when is it going to happen? When are we going to get there? And the truth is, probably never. I don't know, to be honest. It's a good question. All I can say is I can show you this little. So this is the Google IPv6 statistics. I think it's fair to say that Google's probably one of the more used websites in the world. And what they do, if I'll just add that in here, to blow it up a little bit. In fact, let me try that again, because it's. So what we should see really is that, if I can get that to stay, is that our natively accessing IPv6 in Google now, I'm going to try and get the snicker again. We're running at around 30%. Okay, so it doesn't seem much, but over the last 5, 10 years, that has grown a hell of a lot. And you can see there. Okay, just that rate of growth over that time frame, that last really 8 years where it has really picked up. So just to clarify with this this graph, so this is the people that are accessing Google over IPv6. And again, if I could just make this a little bit bigger first. So this is the per country adoption. Move that out of the way for now. So we can see we've got some major differences across the world. So places like Germany, for example, you'll see in the darker green, their adoption is nearly at 50% across their networks. The United States around 40%. Brazil up at like 35%. Where do we sit in the UK? We sit around 30% as well. So recently broken that 30% barrier. But yeah, to answer that question before you ask it, is we'll maybe never get fully across to IPv6, and that's okay. You know, if that's not the end of the world. I'm not sure what happened there. Because we're going to have a number of different transition things in place for a lot of years. So we don't need to worry too much about it. If we ever get there, brilliant. If we don't, it's not the end of the world, because we can keep things running nicely. And it's going to show us, it's going to give us some benefits anyway, which we'll see when we get up to DS Lite shortly. Okay, so a few of the address types that I want to go through. So the first one that we've got is a global unicast address. So what we can think of this as is a routable IP address, one that is routable on the internet, one that is going to be advertised, and we should be able to get everywhere with. Now, it's stipulated that the first 3 bits, so if we see something like this, for example, we might see a /3 being used. All that means is that those first 3 bits, sorry, we're jumping out a little bit here. All that means is that the first 3 bits are fixed. Okay, so it's not the first 3 hex characters that are fixed, it's the first 3 bits. So we've got a 2 here, and I'll give you a full example in a bit. So say we've got our 8421, which is what's making up that 2. We can see that that would be a 0, that would be a 0, that would be a 1. So what IANA have stipulated is that those first 3 bits have to match in order for it to be a global unicast address. So that means that I could, if I wanted to, or if I register my IP address, I could have that as well, which means that I could also start my global unicast address with a 3. So it should be a 2 or a 3 as that first hexadecimal character. Okay, please, if you, then one thing today, because I've seen it a couple of times being taught in an incorrect manner, basically, where it's saying that every global unicast address has got to start with 200, and that's just not true. Okay, so what we might have here is that those first 48 bits, we might call that the global prefix, or something where it's that effect, the global unicast prefix. So this is something that's going to get assigned to us by IANA. And we won't go through all of the different allocations or anything, but obviously it's IANA that is still controlling, ultimately under, giving the commands, to those regional internet registries that are going to be policing the allocation of these IP addresses in a much better way than they did with IPv4. So if you think this time where we've fixed those first 3 bits in position, okay, so think of all the, the scope in the future that we could just change that slightly and just fix the first 2 and give ourselves a lot, more options, each time. So we've got, no worries there. We can actually use the next 4 bits if we wished to distinguish between our subnets. And then generally the last, as I said before, the last 64 bits. Just put that on there. The last 64 bits for the interface. We'll just say we're going to call that 1 in this case. So global unicast address, routable on the internet. Those first 3 bits, not the first 3 hex characters, the first 3 bits need to be locked in position. I've not missed anything here. Right, okay, that's good. Okay, so the next thing that we've got is our unique local address. Okay, so anyone can assign a unique local address. We can think of it as a private address. It's one that shouldn't be routable. Okay, it shouldn't be routable. We're generally going to see it start with FD. Okay, that's the stipulation from IANA. That's what it's got to start with, FD. Everything else, you can do what you like with. Okay, we might see some different scopes being used and etc. We're probably going to see again. We're going to see some, that fourth hex tet being used for subnetting again, and the last 64 bits as that interface again. I'm not going to write 64 bits out. Okay, but it's generally going to be FD. You might see that it's written as FC with a /7, but you'll commonly see that that 8th bit is also turned on, or we get to a D anyway. What we'll also find with most of our IPv6 interfaces, we're going to get a link local address. Okay, we're going to get a link local address, and that's going to be that one that's going to start with our FE80 that we commonly see. Okay, so if you're working on a Windows machine now, if you go and do your IP config or IP config all, you'll see that I'd say 99% sure that your machine will be enabled for dual stack, and you'll see that you've got a link local address that's being assigned to you. Okay, we have the unspecified address, and the way that we highlight that in IPv6 is just with a double colon. Okay, so we can see we've got basically 8 blocks of zeros, and we're just going to demonstrate those with that with a double colon. I'll loop back. Instead of taking up the whole 127/8 range, 16 million addresses, we're just going to use that : : 1. Our multicast addresses are going to be used very commonly, and they're generally going to start with an FF. In fact, not generally, they're always going to start with a FF. Now, the scope or where we're going to send it to, whether it's interface local, link local, site local, will depend on what the numbers are that follow. So if we see, for example, a FF02 : 1, generally we'll use that for that all nodes address. So if I'm sending out my gratuitous app messages, for example, I'm going to be sending them to myself, but if I'm getting a reply to that, then they will use that all nodes address to speak to me, because by default, I'm a node, so I will listen to that multicast address. I will listen for that address. The same as, I would listen to a IPv4 multicast address, as long as that I subscribe to it. And the last one I want to just talk through quickly is a mapped address, an IPv4 mapped to an IPv6 address. I'm just conscious of time a little bit. So what we're able to do, and I think I briefly mentioned it earlier, what we're able to do is put a IPv4 address inside an IPv6 address. We might need to, do that to cross between networks. So this is one way, without tunneling, that we can do it. Although it's kind of a tunnel, it's not. So we might see, and 5. And then what I like to write it out as is X. Is like that. So if you're looking at documentation and you see that W, X, Y, and Z, well, you know that they're not hex characters, don't you? So that, and you'll see that they're separated with dots rather than colons. So that's where we're going to stick our IPv4 address. Now, obviously, we need to change that IPv4 address, don't we? So let's do a very quick example of that. So if we say we've got, I'm making something up. Let's say that. And there's no way I've given myself enough space here, so please bear with me. So for that 200, 128, 192, 200, rest of the zeros. Okay, so if I want to make that first octet into 2 hex characters, then it just means that 128, the value of that now becomes 8. The 64, the value of that now becomes 4. 32, 2, and 16, 1. The value of the second half, the second nibble, if you like, stays exactly the same. We don't need to change the values there. So that means I'm going to generate 2 hex characters from that single octet. So where I've got 8 and 4, I'm going to get 12. So A, B, C. And obviously just 8. I can do exactly the same for all my other characters, which we've got time? Yeah, let's do it. So again, it's going to be 150. So we're just going to say 1, no, 44, 50. Quick maths. Hope you was impressed. Okay, so we're going to have 9 here, and then we're going to have 6. So just for that first hextet, that's all we'll do here. I'll yam those together, and I'll have C8, 9, 6. Obviously, as part of that hextet. Everyone happy with that? I hope so. Okay, Okay, so any questions at all on those address types or abbreviations? I'm just conscious that the chat window's disappeared. So if anyone's been asking me anything, I'm not ignoring you. No. Okay, so any questions on anything that we've covered so far? Okay, so I'm conscious of time, so I'm going to whip through this one, guys. So this is DS Lite, so it's dual stack Lite. So what I mentioned before about you know, are we ever going to get to a stage where we're completely free of IPv4? We don't necessarily need to think in that manner. You know, it's not necessarily a bad protocol, and we can still utilize it. One of the ways that we can utilize it is on certain devices. Now, all of our modern equipment anyway really supports both protocols. Okay, so pretty much every laptop that's made today, every computer that's made today, every router, etc., is going to support a dual stack deployment. It's going to support IPv4 and IPv6. But some of the legacy home network kit maybe won't. Right? So a way that we can get around it is we can actually just stay the same with stay with IPv4 on that home network, and our devices don't need to know any differently at all. So what we're going to do here is we're going to have an IPv4 network Oh, sorry, Julian. I will ignore that. I'm not. You have to tell me what that means. I'm interested. It's like some sort of spy thing going on there from Julian, but that's okay. Okay, so we've got our IPv4 network here. Now, what we're going to have. So this router now. So really, we might know this as a CPE, as a customer premise equipment. We might know it as a soft wire initiator. Not where, soft wire initiator. But what we now are going to call it is basically a B4 router. And that's not a pun, or at least I don't think it is, but it's a basic bridging broadband. Okay, so 4 Bs router, basic bridging broadband. So what it's going to do is instead of this router performing network address translation, it's just going to tunnel my communication in IPv6. So if I'm sending a message across from this device to this device here, I'm conscious you can't see my cursor moving. Hopefully there's not too much of a delay between my pen writing and it appearing. It's going to send that across in IPv6. And let's, obviously we can't do any communication without some sort of connection. Okay, so what we're going to have, what the service provider is going to have here is basically an IPv6 network. So we're going to tunnel our IPv4 address and our communication when we're talking to another IPv4 destination across an IPv6 tunnel. Now, if our devices are IPv6 aware and we're talking direct to IPv6, then we don't need to use the tunnel, okay? But that's the level we're going into today. So with an IPv4, it's going to get stuck inside that IPv6 tunnel, and then it's going to get here. Okay, so you might have heard this before as a soft, I keep calling it software, sorry, just habit, isn't it? Soft wire concentrator. And now you're going to see that referred to as an AFTR, so an address family translation router. Okay, so a really unnecessarily difficult way of saying it's going to translate from an IPv6 to an IPv4. So it's moving between those families, those different address families, address family translation router. So it's going to take that IPv6 tunnel off. So it's the basically the tunnel endpoint. And then it's going to do some NAT, some carrier grade NAT. So it's going to translate that private address range that we've got on this network here to a publicly routable IP address here, so we can access the internet and get our communications to where they need to go. Okay, so that is DS Lite in a nutshell. So what's the benefits of that? Well, as I've mentioned, there's a few. The first one is that we don't need to necessarily make any upgrades to our customer premise equipment, which is great as far as the ISPs are concerned. If they can save themselves some money, that's great. The reality is that they can, for the most part, unless we're really, I apologize if anyone's logging in from the Outer Hebrides, but if we're in places that are maybe not as up to date with their internet technology, you actually find that a lot of those places are more advanced than we are, but that's another story. We don't need to necessarily make those changes on a device, which can be great, as I say, could save us some money. We're utilizing that IPv4 private address space. We've got bags of IPv6 that we can use, but we're going to do it in a nice manner with that IPv6 access network. And with that carrier grade network address translation that we've got, and the AFTR, the address family translation router, the ISPs can get a lot of benefits from that when it comes to, without going into too much depth, kind of privacy and provision and understanding who's accessing what. So they'll actually use probably the tunnel endpoint IDs to distinguish between the IP addresses. Remember, it's going to be point to multi-point. So there's going to be lots of terminations coming in from consumers onto specific points. So those endpoints will be used, those tunnel endpoints will be used to identify the different connections. So think of that session layer in the OSI model, if you like, where we're able to see between the different connections and obviously terminate them. And obviously, if there's anything going wrong or some quality of service needed to be added, then again, we can do that because we can identify it, gives the ISPs that level of control. Okay, any questions on DS Lite? And that is a light overview of dual stack Lite. If there's no questions, what I want to do, we're rapidly approaching time, so let me get into, where are you? Seem to be missing my Eve topology. Sorry guys, bear with a second. I'll get there in a second. And nope, it's not playing. Try again. Right, bingo. Okay, so hopefully you can all see that, guys. So what I've done here is I've just done a very, very basic lab just to show you some of the different commands and workings of an IPv6 network. Obviously, this is using some Cisco devices, and different routers will work in a different way. So one of the first things that I just want to highlight is that with our switches, I don't need to go into that. With our switches, we're not going to need to do anything. Okay, as far as our switches are concerned, okay, we're still going to be building our Ethernet frames. Okay, we're going to be building them in a different way. So one of the things that we're not going to have with IPv6 anymore, because we don't have broadcast, we can't use the address resolution protocol. So we're going to utilize ICMP version 6, and we're going to do what's called neighbor solicitations and neighbor advertisements. So a neighbor solicitation is the same as an ARP request, you know, who has this MAC address, tell me kind of thing. And then that neighbor hopefully will hear that message and send that information back, and you can construct that frame. Now, what we will see is no difference to the switch, or should I say what the switch will see is no different. Just sees that Ethernet destination, Ethernet source. It will make its switching decisions based on that information. It will learn about source MAC addresses and add them to its MAC address table, and it will forward based on, you know, the contents of that destination, of the mapping contained within the MAC address table of that destination MAC address to the interface where it learned it as a source. Okay. Not sure what's going on with the font there. Let's try that again. Okay, so hopefully you can see that a little bit better. So what we'll need to do with some vendor technologies, and I think Juniper, we will need to enable it, and I think maybe HP, some of the HP devices are enabled by default. Certainly with the Cisco's, we'll need to enable for our IPv6 unicast routing. Now, if you don't enable that command in Cisco, and we add an IP address, an IPv6 address to an interface, basically we're making our router, a very, very expensive router, we're making it an IPv6 host. It would answer to messages, but it wouldn't do any routing at all. So we do need to make sure that, you know, obviously check whatever vendors you're using, and enable, make sure that IPv6 is either enabled by default or enable it before you do any sort of configuration. With the Cisco devices, all of the commands are actually very, very similar to the IPv4 commands. We're just going to add IPv6 instead of IP. So if I wanted to see my IP table, and I just do that show IP route, again, you can see we've got nothing there because it's obviously not an IPv4 network. But the difference with just adding that v6 in, we can see the routing table that we've got there. Okay, so very different. I'm just reading James's comment there. Okay, so James, that works automatically once you add the routes. It doesn't need to be enabled as a separate configuration. Is that correct? I'm waiting on you, James. Okay, so yeah, very, very similar. And again, with looking at the interfaces, show IPv6, interface brief, and again, we can see that those are in an up state. So if I have a look now on this Windows machine that I've got here, let's just, it can be a little bit slow, so hopefully not too bad. Okay, so we can see that I've actually disabled the IPv4 stack on this device. Or at least I thought I had. But it's got an IP address. Let me just check something. Come on. Aha, no. Again, sometimes not quite what we want. That's okay. Okay, so we've seen that now that we've just got that information. You can see that we've got an IPv6 address. Okay, if I do an IP config all, so I can see my MAC address for this device. Let's have a look. There's my physical address. Obviously, you can see it's a bog standard virtual MAC address that's been created. But we can see with my IPv6 address that I've been given, we can see what's preferred, see how temporary, etc. It's got nothing to do with that physical address. So we can see that Windows is generating it randomly for us. Okay. If I do a capture, let's start a Wireshark capture. Let's just see if we can get that. Oh, doesn't look good. Panic. No, there you go. It's okay. Okay, so we can see some messages getting sent out there. Let's have a look if I do IPv6. If I go onto this device here and say ipconfig renew and 6. And just like magic, we can see we're soliciting that information. So we can see that router solicitation being sent and that router advertisement coming back. Okay, so you can see that that's where we've actually asked for that information. Okay, so pretty much everything else to do with our IPv6, particularly, you know, obviously there's going to be differences between different vendors, the way things are set up, but the principles of IP addressing and the principles of IP routing, and I say IP meaning everything, are just the same. Okay, so we still are going to see, and hopefully you can see my cursor wagging around, we'll see that we can't put two networks or put the same network on two different interfaces on the same router. Okay, we're exactly the same way as before. When we're talking about IP addresses, we still, if we want to communicate with a node that's in another physical subnet, you know, that we're separated between two routers, we need to have a different network ID so that we know that we've got to send out traffic to the default gateway. And we're not going to be sending out neighbor solicitations within the network looking for someone that isn't there. Okay, and vice versa. Okay, so if I want to communicate with someone in the same in my same network, then we need to have the same network ID with my IP address, IPv6 address, and the length that I have. When it comes to routing protocols and learning about routes, again, it's going to be exactly the same way. You know, there may be some subtle differences to how we configure static routes, depending on the vendor. We may be able to use the link local interface, for example. We might need to actually specify what physical interface to use. Okay, but the actual principles, you know, so we can statically assign those routes. We can add those static routes in the same manner. We can dynamically learn them with routing protocols, even though they'll be slightly different routing protocols. You know, if anybody is using RIP, it's the next generation of RIP-NG. Obviously, hopefully you're not. Or we're more likely to be using something like OSPF. Well, we'll be using version 3 as opposed to version 2 that we used with IPv4. Okay, so bags of information there, guys. I hope that's been useful for you. I'm just going to quickly go back to my PowerPoint. I don't think there's anything else that I wanted to cover. Let me just have a quick check. Yeah, I just wanted to make that point about, you know, about quartets and hextets. I don't think I mentioned that. So obviously hextet is what it's commonly referred to as, but you can have a little look on Reddit and you'll see a massive big argument and discussion about what to call an IPv6 hextet. If it's important to you, have a look at that. Other than that, that's pretty much all I've got for you. So this is probably a good opportunity, Holly, for any Q&As. I didn't see any.
No, we haven't got any, but if you do have any questions or Q&As or anything that you want to ask Brian, then just pop them in there. But no, well, I'll do my little closing speech. So thank you all for joining us. We hope you enjoyed the session. And remember, if you have any other webinar topic suggestions, to get in contact with us and we can have a look into it. And also, if you could please remember the very, very short survey after you leave the webinar, then we really appreciate it. Shameful plug there. So both myself and Brian will stay on the call for a few extra minutes for any last minute questions you have. But if not, thank you very much for attending. And we hope to see you for our next training session on DNS. And then I'm just going to pop the links in the chat, all the links I've mentioned. So you've got the future events where you can register for the DNS, all our webinar, past webinar recordings, and then our contact details if you need it. But yeah, so we hope you all have a lovely rest of your afternoon. If you're in the UK, we've actually got some glorious sun, so I hope you get to enjoy that over the weekend.
Yeah, I think it's just about gin o'clock, isn't it?
Oh, it's always gin o'clock. 5 o'clock somewhere.
Yeah. Yeah. So thank you, James. I saw your comment there, and thanks for the little information on the junipers. Always useful. So if there isn't any more questions, guys, obviously I will tidy up the presentation that I went through today on the whiteboard, and I'll send that to Holly, and I'm sure she'll make that available for you guys if that's something that's useful for you, something you can either use as a reference or again for any studying. And of course, you know, we go into a lot more depth on a number of different topics at SNT. So if there are, you know, courses that you're interested in, you know, get in touch with us, and we can go from there. And I think other than that, Holly, just to say that obviously the next session, that's with my colleague Rob Minchell, who's taking DNS. Is that next Friday, the 7th? Yeah, of course it is.
Yeah.
First today. So Rob's a really experienced trainer. I'm sure he's got a pair of trainers. Really experienced trainer, and yeah, what he doesn't know about DNS, you can write in the back of a fag packet.
Very lovely. Well, I don't see any more questions, so we'll end it there. Thank you very much all for attending. Should you need to contact any of us, or if you want to get in contact with Brian or anything, just email us at marketing@linx.net and then we can connect you. But if that's it, I will end it there. So thank you very much, and hope to see you all again soon.
Yeah, great. Thanks everyone for attending, and have a great weekend.